Hello, Professor. For this final Jedi assignment, I decided to do, have you ever wondered how a balloon can just stick to your sweater? And I chose this because this was the first week, and I feel like this topic was pretty interesting to me, and it just shows how everyday life does involve physics. So now to understand this process, we have to understand how electrons and protons interact with each other. So an electron is negative charge, and you can see that right here in the red. And then a proton is a positive charge, and you can see that right here in the green. And this image right here that I have gotten from online states that it demonstrates how the negative charges repel each other, and the positive charges also repel each other. And so these protons and electrons, they actually attract each other. So this interaction is what makes the sweater and balloon able to interact. And you can see here in the center of an atom is a proton, this little blue, and then the outside of an atom is an electron. So these electrons surround it. And from this image, we know it's an oxygen atom because there's 8 electrons around it. And this just shows that the electrons are kind of easy to pick off, but you're going to want to keep the proton in the center. So this will make sense for our next image, how in this process with electron forces, we have electrons being taken off in order to create this force. So in order to do this and to create this interaction between to create this electric force, we have to do several different types of ways in order to create this. So first, you can do charging by friction or by contact or by induction. So charging by friction would be rubbing a positive charged object against a negative charged object. So an example of this would be rubbing a balloon against wool or a human. And I said wool because that's an example of having like a wool shirt or something like that. And the balloon is rubber, so that would be a more negative charged object. And then the human, such as like if you rub it against your hair, would be a positive charged object. And so rubbing these two objects together creates friction and allows them to be attracted more to each other. And we'll demonstrate that soon. And then charging by contact would be using a negatively charged object and just simply touching it to an uncharged object. This non-charged object will then become negatively charged as the electrons are transferred from one object to the next. So an example of this, which was done in the book, was a rod to a sphere. So the rod touches a sphere, and the sphere will spread these electrons around the whole object, making it negatively charged. So just one simple touch can cause the transfer of these electrons to the sphere. And the last one would be charging by induction. This would be, again, an example of hovering the rod over the sphere in order to make the sphere charged. So the rod does not have to touch the sphere, but because we do have these interactions between each other, it's just able to transfer, through the air. It doesn't even have to even touch, which is cool. But for this example that I did with the balloon and the sweater, we're doing charging by friction. So I wanted to go to this website because it makes the most sense to be able to see it here. And you can see how when you rub this on, you can hear the little dots connecting, but that's the balloon. It doesn't actually make that sound, of course, but that's a balloon picking up these electrons. And see how the sweater does keep its protons? So we're just transferring electrons around. So now that this balloon has collected all of its electrons by friction, it's become charged, and you'll see when we let it go, I let it go, and it just wants to float back to the sweater, which is what you usually see if you've done this in person. And then you can see this balloon still has still has protons, but it's just not as many as electrons, which causes it to be charged. So now I'll go back to here, and then a way to apply this to physics and actually calculate this would be Coulomb's law. And Coulomb's law is force equals Coulomb's constant times Q1 times Q2 divided by R squared. And to understand these, F stands for force, and force is a vector that measures magnitude and direction. And its SI units is newtons, which is also just known as N. And K is an electric constant. It's Coulomb's, also known as Coulomb's constant. And this constant is going to be 9 times 10 to the 9th. And its SI units are newtons times meters squared divided by Coulomb squared. So you can see I have that right here, the simplified version of it written out. And Q is the value of point charge, and its SI units is coulombs, so C. And then R is the radius, and the radius is the distance from the center of a circle to its edge. So nothing too complicated there. Its SI units is meters, and it's just M. And we'll go more into Q1, Q2 in the problem, but this Q is the same. It's just showing that you have two different point charges that you're multiplying by each other. So next is question number 3 that I did, and this states, in a vacuum, two particles have charges of Q1 and Q2, where Q1 equals 3.3 microcoulombs. They are separated by a distance of 0.2 meters. And particle 1 experiences an attractive force of 4.3 newtons. What is the value of Q2 with its sign? So with its sign is important. You can see that I end up getting a negative answer, and we'll get to that at the end. But first of all, to be able to understand what equation we're going to use, it was pretty straightforward because we involve Q1, Q2. We have Q1. They want us to find Q2. And they give us a distance in meters, so we know that's going to be our radius. And then they also give us force. So I know that I'm going to be using Coulomb's constant, or Coulomb's law, which is force equals K times Q1, Q2 divided by R squared. And I put these absolute value brackets here because at the end of the problem, you'll see how we get a negative answer, but our force is positive. So we do need these absolute values because that just demonstrates how we actually get a positive force. So I wanted to get Q2 alone, and we don't actually have to involve the absolute value brackets in our equation down here. But I have to first multiply R squared both sides. So I get force times R squared equals K Q1 times Q2. And then I have to get Q2 by itself, so I divide KQ1 on both sides. So I get Q2 equals force times radius squared divided by K Q1. So now I have my equation. And before I go down here and plug it all in, I wanted to get something straight first, which was Q1 was given to us in microcoulombs. And we know that just to make things easier, we could convert it later, but we could just convert it now. Well, actually, we'd have to convert it now for things to cancel out easier. But I had right here that my SI unit's coulombs, so it's not microcoulombs. So I have to convert this to coulombs. So that's pretty easy. 1 microcoulomb equals 1 times 10 to the negative 6 coulombs. So I take 3.3 microcoulombs and multiply it by 10 to the negative 6 coulombs, and I get 3.3 times 10 to the negative 6 coulombs. So now I can plug this in to my equation, and I get Q2 equals force, which would be 4.3 newtons, times 0.2 meters squared, divided by our K, which is our Coulomb's constant, times our new coulombs, or our new Q1, which is just in coulombs, not microcoulombs. And a way to know that we're actually on the right track, because we want coulombs, is I started canceling out my variables. So my newtons would cancel out because they're divided by each other. And then my meters squared cancel out, so that's good. And then my coulombs, 1 coulomb would cancel out. So we take that square away and leave us with 1. So I end up getting negative 5.8 times 10 to the negative 6 coulombs after solving all that math. And I just had to add the negative charge on because right here you can see it states attractive force. So we know that we're dealing with two different charges. So we know we're dealing with an electron and a proton because they're attracted to each other. So that kind of wraps up everything that we learned, that's how we can solve for that. Because they attract each other, but we also know our force is positive because we're just looking at those attractive forces. So in conclusion, the balloon sticks to our sweater because we have charged it by friction. The balloon collects the electrons from the sweater, which leaves the protons on the sweater. Which causes the positive and negative charges to attract each other. And I put this cute image, and I got it from I made it from ChatGPT. But it just shows a proton being attracted to an electron because opposites attract. And this also can be applied to sticking a balloon on your head, or when you walk and then all of a sudden, or you're like shuffling your feet and then all of a sudden you touch somebody and you get shocked. That's due to these forces. And my references, I did the website that we had in class for the demonstration. And then the slide 7 was ChatGPT. Thank you.